Imagine you're standing in front of two sealed envelopes. Both contain money. You know that one envelope contains exactly 10 times more money than the other, but you have no idea which is which. It could be $3 and $30 or $5 million and $50 million. The amounts are completely unknown to you. Someone offers you a simple choice. Pick one envelope and keep whatever's inside. You reach out and grab one at random. But just as you're about to leave, they offer you one final option. You can switch to the other envelope instead. Should you switch? This deceptively simple question is about to lead us into one of the strangest paradoxes in mathematics. A paradox so bizarre that it will make you question whether our most basic mathematical tools can be trusted. At first glance, the situation seems perfectly symmetrical. You chose randomly, so there's no reason to think one envelope is better than the other. But let's imagine for a moment that you're allowed to peek inside your envelope before deciding whether to switch. You open it and find $40. Now you know something crucial. The other envelope contains either $4 or $400. Since you don't know which scenario you're in, you might reasonably think the other envelope contains, on average, about $202. That's significantly more than your $40. So switching seems like the smart move. But here's where things get weird. This logic works for any amount you might find. If you had found $100, the other envelope would contain either $10 or $1,000, averaging $505, which is still more than your $100. If you had found $1,000, the other envelope would average $5,050, beating your $1,000. No matter what amount you discover in your envelope, the math suggests you should switch. And if you should switch regardless of what you find, why bother looking at all? You should just switch. Period. But wait, this conclusion is absurd. The envelopes are identical and random. There's no magical reason why one should be better than the other. The problem with this first version of the paradox is that it's too vague. We don't know what amounts are actually possible or how likely each scenario is. Without this information, we can't analyze the situation properly or even simulate it on a computer. Let's fix that. Here's a mathematically rigorous version that captures the same essential paradox while providing all the missing details. The possible amounts in the envelopes are specific pairs, either $1 and $10, or $10 and $100, or $100 and $1,000, and so on. An infinite series of consecutive powers of 10. There's a 1/2 probability of getting the $1 and $10 pair, a 1/4 probability of getting the $10 and $100 pair, a 1/8 probability of getting the $100 and $1,000 pair, and so on, with each subsequent pair being half as likely as the previous one. These probabilities sum to exactly 1, as they should. You know all of this when making your decision. When you pick an envelope, you choose each of the two envelopes with equal probability, 50% chance for each. We can organize all this information in a table. Each cell shows a possible amount you might get, along with the probability of getting that amount and what would be in the other envelope. Here's where the probability calculation gets interesting. Let's trace through exactly how you might end up with $10 in your envelope. Scenario 1. The $1 and $10 pair. The probability of getting this pair is 1/2. Since you pick randomly between the two envelopes, there's a 50% chance you get the $10 envelope. So, the probability of getting $10 this way is 1/2 times 1/2 equals 1/4. Scenario 2. The $10 and $100 pair. The probability of getting this pair is 1/4. Again, you have a 50% chance of picking the $10 envelope from this pair. So the probability of getting $10 this way is 1/4 times 1/2 equals 1/8. The total probability of finding $10 in your envelope is the sum of these two possibilities. 1/4 plus 1/8 equals 3/8. This pattern holds for every amount except $1, which can only come from one scenario. Each amount appears in exactly two different pairs, once as the smaller amount and once as the larger amount, and the probability of getting that amount is the sum of the probabilities from both scenarios. Now we can systematically analyze what you should do based on what you observe in your envelope. If you see $1, this can only come from one scenario. You got the smaller amount in the $1 and $10 pair. The other envelope must contain $10. You should definitely switch, gaining $9. If you see $10, this is more complex. You're in one of two scenarios. You got the larger amount in the $1 and $10 pair with probability 1/4. You got the smaller amount in the $10 and $100 pair with probability 1/8. Given that you observed $10, we need conditional probabilities. The probability you're in the first scenario is 1/4 divided by the sum of 1/4 plus 1/8, which equals 2/3. The probability you're in the second scenario is 1/8 divided by the sum of 1/4 plus 1/8, which equals 1/3. So the other envelope contains either $1 with probability 2/3 or $100 with probability 1/3. On average, that's 2/3 times $1 plus 1/3 times $100 equals $34. Since $34 is more than your $10, you should switch if you see $100. By similar reasoning, the other envelope contains on average $340, which beats your $100. You should switch. The pattern is clear and disturbing. No matter what amount you observe, you should always switch. The expected value in the other envelope is always higher than what you have. If you should switch regardless of what you observe, then you don't need to observe anything at all. You should just switch, period. But here's where the paradox becomes truly mind-bending. We can use the exact same logic to prove the opposite conclusion. Suppose instead of looking at your envelope, you're allowed to peek at the other envelope before deciding whether to switch. If you see $1 there, your envelope must contain $10. You shouldn't switch. If you see $10 there, your envelope contains on average $34. You shouldn't switch. Following this logic, you should never switch, regardless of what you observe in the other envelope. So we have two supposedly rigorous arguments. 1. You should always switch. 2. You should never switch. Both can't be true. Something is seriously wrong with our reasoning. To resolve this paradox, we need to dive into the mathematical machinery of probability theory. Let's define our random variables precisely. Let x equal the amount of money in the envelope you picked. Let y equal the profit from switching, that is, the amount in the other envelope minus the amount in yours. Our earlier analysis showed that for any specific value you might observe for x, the conditional expected value of y is positive. In mathematical terms, the expected value of y given x equals x is greater than 0 for all possible values of x. This is where we made our crucial logical leap. We reasoned that if the conditional expected profit is always positive, then the overall expected profit must also be positive. This seems to follow from the law of total expectation. The expected profit from switching equals the expected profit given you found $1 times the probability of finding $1 plus the expected profit given you found $10 times the probability of finding $10 plus the expected profit given you found $100 times the probability of finding $100, and so on for all possible amounts. Since all the conditional expected values are positive and all the probabilities are positive, the sum should be positive too. Therefore, expected value of y is greater than 0, which means you should switch. This reasoning appears ironclad, but let's check it by calculating the expected profit directly from the basic definition. Let's list all possible profits and their probabilities. If you pick the $1 envelope, your profit from switching is $9 with probability 1/4. If you pick the $10 envelope from the $1/$10 pair, your profit is negative $9 with probability 1/4. If you pick the $10 envelope from the $10/$100 pair, your profit is $90 with probability 1/8. If you pick the $100 envelope from the $10/$100 pair, your profit is negative $90 with probability 1/8, and so on. The expected value should be 1/4 times $9 plus 1/4 times negative $9 plus 1/8 times $90 plus 1/8 times negative $90, and so on. Notice something strange. Each pair of consecutive terms adds up to 0. We get $9 minus $9, all divided by 4, plus $90 minus $90, all divided by 8, plus $900 minus $900, all divided by 16, and so on, which equals 0 plus 0 plus 0, and so on, which equals 0. So the expected profit from switching is 0, not positive. We now have 3 different proofs. 1. The expected profit is positive, so you should switch. 2. The expected profit is negative, so you shouldn't switch. 3. The expected profit is 0, so it doesn't matter. Clearly, something fundamental is wrong with our mathematical reasoning. To understand what's happening, we need to explore a subtle but crucial aspect of infinite series. Consider this famous example, the alternating harmonic series, 1 minus 1/2, plus 1/3, minus 1/4, plus 1/5, minus 1/6, plus and so on. This series has a well-defined sum, approximately 0.693, which is the natural logarithm of 2. But here's the shocking part. If we rearrange the terms, we can get a completely different answer. Suppose we group the terms differently. 1 plus 1/3, all in parentheses, minus 1/2, plus 1/5, plus 1/7, all in parentheses, minus 1/4, plus and so on. This rearranged series converges to a different value, approximately 1.04. Same terms, same operations, different order, completely different result. This bizarre behavior occurs when both the positive terms and negative terms of a series sum to infinity. This is exactly what's happening in our envelope problem. When we calculated the expected profit directly, we wrote 1/4 times $9 plus 1/4 times negative $9 plus 1/8 times $90 plus 1/8 times negative $90, and so on. But this ordering is arbitrary. There's no mathematical reason why a loss of $9 should come before a profit of $90 in our calculation. The crucial issue is that in our profit series, the sum of all positive terms is infinite. The sum of all negative terms is negative infinite. This is precisely the condition that makes infinite series behave pathologically. Different orderings can give us different results, and the series doesn't have a well-defined sum. Our random variable y, the profit from switching, is one of those rare mathematical objects that simply doesn't have an expected value. Not positive, not negative, not zero. It just doesn't exist in any meaningful sense. This is why our use of the law of total expectation was invalid. The law states that if a random variable has an expected value, then you can calculate it using conditional expectations. But if the expected value doesn't exist, the law doesn't apply. We committed a mathematical sin by assuming the expected value existed when it actually didn't. This allowed us to prove contradictory conclusions. So how should we make decisions when expected values don't exist? We need different criteria. Let's try a different approach. Suppose you're the kind of person who particularly dreads missing out on a large amount of money. You want to minimize the probability of losing more than, say, $500. Under the don't switch strategy, you lose more than $500 only if you picked an envelope with $100 or more when the other envelope had the larger amount. The probability of this is 1/8. Under the switch strategy, you lose more than $500 only if you originally picked an envelope with $1,000 or more when it had the larger amount. The probability of this is also 1/8. Both strategies give you the same probability of experiencing this particular type of regret. This makes perfect sense given the symmetry of the problem. The two-envelope paradox teaches us something profound about the limits of mathematical reasoning. Expected values are incredibly useful tools. They're used everywhere from finance to engineering to biology. But they're not universal solutions. Some situations push us beyond the boundaries where our standard mathematical tools work reliably. When we encounter infinite series where both positive and negative terms sum to infinity, our usual intuitions can lead us astray. The paradox also highlights the importance of mathematical rigor. Our common sense reasoning about averages and expectations seemed perfectly logical, but it contained a subtle flaw that led to contradictory conclusions.